In the textbook, we've derived the Helmholtz equation, and we've mentioned that that derivation was only valid in case you had uniform media. Now the question is, what happens if you have non-uniform media? Which step exactly in the derivation is where it breaks down? So pause the video to go through the proof and then figure out which step is problematic. Let's just go through the proof once more, step by step. So the first thing we do is we write down the curl equations. So the first thing involves the curl of the electric field, which is minus j omega mu h. And we're going to assume here that we're still working in non-magnetic media, so mu is a constant. Second equation, curl of h, j omega epsilon, and this time it's important to realize that epsilon can be a function of r, so let's make that explicit. So these are the two equations we start from, and the first thing we did is we took the curl of this first equation. That brings us to curl of the electric field is equal to, then this minus j omega mu is a constant, so we can just bring that out of the curl, since we have non-magnetic media, and then we have the curl of h. Now, the good news is we know what the curl of h is, so that's given by this equation, so we can just substitute what we have over here in that equation over there. So there's nothing suspicious there, nothing fishy. That just becomes minus j omega mu, and then we have j omega epsilon, still a function of r, times the electric field. So far so good. We've done nothing that wouldn't work anymore in case epsilon is a function of r. So let's see what happens next. The next thing we did is we tried to simplify or expand this double curl here. So we know from vector calculus that the curl of the electric field in this case is equal to the gradient of the divergence of the electric field minus its Laplacian. Okay, and then we proceeded to get rid of this first term involving the divergence of E, and the argument there was that there's no sources, so that equation should be 0, and therefore we can drop that term here. Here we need to be a little bit careful, because the most general form of that equation, this divergence equation of Maxwell, is actually that the divergence of the dielectric displacement is equal to rho, the charge density, which is 0 in case there's no charges. However, we know what the relationship between D and E is. D is actually equal to epsilon E. Okay, so here you see what's going on. In case epsilon is no longer a constant, we cannot bring epsilon outside of the curl to conclude that the divergence of E is equal to 0, and therefore the cancelling of that particular term. So this is what goes wrong in case we have an epsilon which depends on r. We can no longer conclude that that term is equal to 0. But no need to despair, because in a later chapter we will derive an equation that is perfectly valid in case epsilon is also a function of r. So stay tuned for that.